In the fairy tale Goldilocks and the Three Bears, a little girl named Goldilocks tastes the bear's porridge, finding one too hot, one too cold, and one just right. She also tries out their chairs and beds, each time finding one that is just right. In the world of high-density backup power, lithium-ion batteries often discharge too slow and have limited charge-discharge cycles. Meanwhile, supercapacitors have limited energy density. In today's Tech Chat, Eaton discusses their hybrid supercapacitor technology that combines the features of both batteries and supercapacitors to make a solution that may be just right to meet your backup power needs. Welcome to Tech Chat, where we get to learn firsthand from industry experts about important topics in the electronics industry. Today's episode is sponsored by Mouser Electronics, and we are happy to welcome Akos Labati, who is a senior field applications engineer with the electronics division at Eaton.
Hello, everyone, and hello, Dale. Thank you very much for the invitation for this chat. And I hope that I'm going to be able to teach you something about how to power IoT devices, especially the battery-powered ones.
I'm looking forward to hearing about it, so let's get started.
So before we get into the main topic, which is about the IoT-powered devices, which are battery-powered, and certainly poses some challenges in terms of the designing, and that's what we're going to discuss about. Let me introduce our company, Eaton Electronics. So Eaton Electronics is part of the greater Eaton, who is manufacturing already a lot of IoT devices and provides a lot of solutions. But we are actually from component manufacturing part of Eaton as the electronics division, who are manufacturing passive electronics components, namely magnetics, supercaps, and circuit protection, which are all available by Mouser as well. And we are specialized for any kind of powering challenges in terms of the power conversion, in case of the power storage, and in case of the protection devices as well.
Excellent. Well, let's dive into our discussion today about supercapacitors.
When it comes to powering devices, especially off the grid, we obviously need to have some energy storage units, which are normally categorized in terms of energy density and power density. So that's what the Ragon plot is talking about. And what you can see here is basically overview of the most common energy storage devices, starting with the fuel cells, which may have a very high energy density, but poor on power density. And at the other side, there are the supercapacitors, which are extremely high on power density, but lacking a bit of energy density. In between, you can see all the battery technologies topped with the lithium-ion technologies. That's obviously the most advanced technology, and that has basically the highest energy density and very high power density at the same time. And we're going to introduce today a new technology, which we actually started to manufacture about 1.5 years ago. It's a quite recent development, and it's a true combination of lithium-ion and supercapacitor technologies. And we're going to dive into that as well.
Yeah, so for people who are not quite familiar with this plot, basically on the vertical axis, it's just how much energy you have, and the horizontal axis is how quickly you can deliver that energy, right?
Exactly.
And so today's discussion, we're going to be in that lower right corner of the graph.
Yeah, we're going to touch a bit on the battery technologies as well, which definitely needed for the IoT devices to be powered. But we're going to put a bit more focus on the extension of the battery lifetime, which is obviously challenging and actually a critical item when it comes to the overall cost and the size of this kind of devices.
No, that makes sense.
Yeah, Eaton is manufacturing already more than 20 years supercapacitor products, which you can see here just as a quick lineup. So we actually develop for the industry coin cells as well as small cylindrical cells. These are the biggest chunk of our manufactured products. And we recently introduced the hybrid cells that is basically the most advanced technology and getting the most attention at the moment. And obviously we have the larger cells and modules and even the systems for like grid storage, but that's something which is out of the scope for today, because the scope for IoT is mainly coin cells, small cylindrical cells, and the hybrid cells. And we're going to dive into that a bit more in detail in the coming minutes.
It really shows off the breadth of coverage you have there. I mean, it's 5 orders of magnitude in capacity.
Well, yeah. This obviously in terms of the energy and the power density, so they are covering all the basically the yellow spot on the diagram plot, which is displayed as the supercapacitors. Obviously, coin cells are normally delivering milliwatts or microwatts of power, while the modules and the systems are for the megawatt power. So this is obviously quite a big range. But normally, what we can say is that this kind of technologies, supercaps and the hybrid supercaps, are normally used for quick burst of energies to be delivered. In an economical scale, we talk about 30 seconds, or for the hybrid cells, we talk about just a couple of minutes. Everything beyond that level of, let's say, autonomy times is for batteries, basically.
Right.
Then let's dive a bit into what are supercaps versus hybrid capacitors or hybrid supercapacitors and the batteries. Here, what you can see is basically how the quick description about how EDLCs, like a supercaps work. EDLC consists of or means electrolytic double layer capacitors. So in case of the EDLCs or supercapacitors, or maybe called like gold caps or ultra caps, the technology consists of two identical electrodes, which is a porous carbon activated carbon electrode, and there is separator in between to physically isolate the two terminals. But actually, this porous material is impregnated with a kind of electrolyte that is dissolving some special salts that is creating an ionic environment. The way it works is an electrostatic charge and discharge process. So it's very similar to the standard electrolytic capacitors or any kind of capacitors, but the only difference is that you have a huge terminal because it's a porous material, which is covered by so-called Helmholtz layer. It's a special insulating layer coming from the type of electrolyte we are using. So that's why we talk about the molecular size of distance and the huge surface. So this is why electrolytic double layer capacitors can store 5 to 10,000 times more energy than a standard aluminum electrolytic capacitor, for example. So it really works the same way. So in case of the charge and the discharge, it's very easy electrostatic process, no degradation practically. So we normally rate these capacitors for a million or millions of cycles to be delivered or charge and discharge. It's a very long lifetime device as well. It though it cannot really store that much energy, and as you can see as a disadvantage, the discharge curve is pretty linear. So whenever you start to discharge, this capacitor is dropping the voltage pretty fast. So normally, you need the power converter, or you need to set your circuit voltage levels or voltage range according to the supercapacitor's delivery range, which is time to time can be quite challenging.
Yeah, and the fact you have no chemical or even a mechanical reaction is really what sets supercaps apart from batteries or flywheels. With those characteristics in mind, how does that then compare to a more traditional battery?
You can see a general construction of lithium-ion batteries, which is a rechargeable battery. On the anode side, you see that it's a lithium-doped graphite. On the cathode side, there is a lithium metal oxide. It consists of different type of metal compositions. And here, actually, what's happening is a chemical reaction. So it's a standard. It's a battery. So there is a chemical oxidation happening during the charge and the discharge cycling, and the large ions are traveling through a separator. So you may remember, so we are using for a supercap a similar separator, even though it's a different material. So we are using basically a cellulose-based, very porous separator. While for the lithium ions, the separator is it's a stronger construction of some type of plastic material with a specific pore size, and basically that's what sometimes limits the charge currents and having actually some degradation, because a lot of numbers of ions is to pass through the separator during the charge and the discharge cycles. So as you can see, the lithium ions all pass through back and forth, and they are getting oxidized as well sometimes at the cathode side. and that might have some buildups that may cause further degradation for the batteries. So that's why even though they can store a lot of energy, their cycle life is limited to, let's say, 1,000 to 3,000 cycles. Newer technologies may allow 5 to 10,000 cycles as well. Despite of these disadvantages, lithium ion poses, let's say, from the circuit's point of view, a pretty good type of discharge curve. So if you see the discharge profile using a constant current discharge, the lithium ion cells maintain the voltage pretty stable for quite a long time. So in terms of powering like an IoT device or like any type of circuit which runs in about in the low voltage range, the lithium ion is an ideal energy storage device which often can be directly connected to the loads.
That flat discharge profile is certainly a key reason that lithium ion batteries have found such universal use, because you just plug them into a circuit and they run without any extra circuitry a lot of times. All right, so now most of our engineering audience has heard of both supercaps and lithium ion batteries, but what is a hybrid?
Hybrid supercapacitors, or often referred as a lithium capacitor, is a true combination of the two technologies in the same body. Actually, these are normally cylindrical devices, pretty much similar to the lithium-ion batteries, where the anode is actually the same that are used in the lithium-ion technologies, and the cathode is the same as we are using it in the supercapacitor technologies. So it's really a true combination, which gets us very interesting combination and the performance aspect. So in terms of the discharge curve characteristic, it's quite similar to the supercapacitor. So in terms of the method to calculate the discharge profile or determine the discharge profile, they're dropping the voltage, but not that significantly than it would be for the standard supercapacitor. So this hybrid capacitors can align to most of the circuits without any converters to be applied. And in terms of, let's say, the cycle life, this results in incredible 500,000 cycles. That's even hard to imagine, but the trick is the following. So we are using still actually separator than we are using for the supercapacitors, which are quite porous, and there are no actual large ion movements through the separator, and there are no oxidation at the cathode side. So actually, this is just about to undope a couple of lithium ions from the structure, and during the charging, we are redoping it, and while we are actually releasing the electrons to the cathode side. So it's a combination of an electrostatic. It's rather like an electrostatic process. Actually, it can be. We could tune this product rather to like a battery or rather to like a supercapacitor. The way we call it, or the reason why we call it hybrid supercapacitor, is it's really like a supercapacitor with a very high power density and as well as a very long cycle or very high cycle life.
So the LIC there in your header, you said that is lithium capacitor is what you call it as well?
Yes.
Interesting. And so by preventing that depth of discharge then, because you're trapping the lithium ions on the one side of that separator, that's what then gives you that high cycle count?
Yes.
So how does then that overall performance of a hybrid then compare to a more traditional supercap?
Well, if we do a comparison, which the major differences is that the traditional supercaps have some advantage on the lifetime. So it's normally like a 20 years device, while the hybrid supercap is like a 10 years device at the same conditions. And the traditional supercaps can do a bit more cycling, which is normally not really required by the applications. And they work better on the broad temperature range. So they can really get down to minus 40 Celsius degree with very high power density still remains. And while the hybrid supercapacitors have much higher energy density, so it has an incredible 8 to 10 times more energy storage capability in the same form factor as traditional supercapacitors, and have a much lower self-discharge. So while supercaps are normally self-discharging in days or weeks, hybrid supercapacitors discharge only in months or years. So that's quite incredible.
Yeah, it really is. So is it fair to say then they operate more like the supercapacitor with respect to the cycles and how quickly they can give out their energy, but they're more like the battery as far as the thermal characteristics in operation?
Yeah, if we do a comparison between batteries and the supercapacitors, you can see that the lithium-ion batteries still have an advantage on the energy density. So it 3 to 8 times more energy density than a hybrid supercapacitor, and the cost per watt hour is obviously lower than the hybrid supercapacitors. But the hybrid supercapacitors provide actually kind of like double of the lifetime versus a light lithium-ion battery without taking into consideration the cycling, and have obviously much longer cycle life. And what I didn't mention yet about is about safety. So no thermal runaway, no short circuit causing fires, or no kinds of dendrites growth and so on, which may happen at the cathode side, and makes basically the most trouble with the lithium ion technology is present in the hybrid supercapacitors, because we are not using any metal oxides inside. So that makes the hybrid supercapacitors ideal for safety critical environments as well.
Yeah, and as anybody who has tried to ship electronics, that's a pretty big issue.
Yeah, it certainly is. So one is basically the shipping, and there are certain environments where lithium ion technology has a true benefit, but in terms of the safety, they need to actually use very advanced battery management systems that makes basically the cost of the solution very high.
Oh, that's an excellent point too.
Yeah, here you just can see basically a practical comparison between a supercapacitor, similar size hybrid supercapacitor, and two different battery technologies, lithium ion and nickel metal hybrids. So you can see the total stored energy is obviously larger for the battery technologies. But in case of the peak power, you can see that 60 by 25 millimeter device can deliver like 36 watts versus 10 watts of a slightly larger lithium ion, which is a professional lithium ion cell actually. And if we talk about the energy transfer life, that's basically where the most important aspect may play, especially if the application is requiring a lot of charge and discharging cycle, a lot of energy swing, and that's certainly the big plus in terms of the new hybrid technology. When we look at the operating temperature range, I mentioned earlier that supercaps are unbeatable for low temperatures. So at minus 40 degree, we may have a 1.5 times ESR increase. We have ESR. So when we consider 125 watts at minus 40 Celsius degree, it can still deliver like 80 watts, which is quite useful. And in case of the hybrid capacitors, they are obviously having a bit of the battery-like behavior at the lower temperatures, but not that much as the standard battery technologies. So we have a series that is rated to minus 25. The higher temperature version, the HS series, is rated to minus 15, which is pretty well fitting for most of the applications, even if they go to sub-zero temperatures.
And that's an important conclusion you have there at the bottom that the hybrid is going to be a better solution for certain applications. So it kind of gives the designer who's building their system a new toy in the toolbox, basically, to fit the application. And rather than having to do a battery or do a supercapacitor, sometimes both, they get paired together because they have unique characteristics. So bringing them into one new device is certainly an interesting opportunity for people.
Yeah, definitely. That was quite fun to see when we checked on the Mauser POS and who were the first buyer of this supercapacitor cells. As soon as you had them on stock, and these were like all kinds of universities and technical schools and so on. So I think everyone wanted to get a hand on some of these devices and start to do some experiments. And we got pretty good feedback from the market, and obviously the professional companies were also trying and started to use this already in a larger numbers as well.
And that's a good segue for us. Now you've kind of given us a background on the chemistry and the differences and the performance characteristics. Let's talk about some of the applications.
So here you can see an outline of the different kind of wireless IoT protocols that certainly require some power if the device is not connected to the grid but battery powered. There is certainly something which you are very familiar with, which probably is the Bluetooth and the Wi-Fi. Everyone is using it all over the place, in our homes, in our cars. These are the communication channels that does not require any type of booster because they are quite stable in terms of the power consumption. So you either need a big battery or a smaller battery, depending on how long time and how long distance you want to transmit. So they are pretty well working with lithium ion nickel metal hybrid technologies. While there are the last two ones, LoRa and the narrowband IoT, that are transferring not only just to like 100 meters away or 100 yards away, but all the way up to hundreds of kilometers, like the narrowband is capable for. And certainly the communication and the transfer energy that is needed and transfer power that is needed to cover these ranges requires higher amperes at the lower voltages where this device is normally operating, so about 3.6 volts. So the LoRa normally consumes between, let's say, 20 to 150 milliamps. So like a typical consumption is about 40 50 milliamps, and the continuous consumption is about 50 microamps for the device, depending on what the device is doing. It may be a sensor, it may be an actuator, and here actually supercaps are optional to the battery. So anyway, you need a battery. It may be a lithium ion, it may be a lithium primary or tiny battery. It can be a nickel metal hybrid technology as well. And we're going to see an example later on how to distinguish different type of requirements, or what is really the decision point where supercaps are necessary or helping the circuit, or the battery is enough. While there are the narrowband IoT systems, which are GSM or GPRS based, normally in Europe, I can tell that 2G is obviously obsolete, so they are mainly using the 3G or the 4G networks. That requires obviously higher powers, depending on how distant the transmission towers or receiving towers may be. So it's from 200 milliamps all the way up to 2, even 3 amps we have seen for some asset tracking devices. For normally the device, it's less than 100 microamp in a sleep mode that is required to operate. So obviously there are some normally primary lithium cells, lithium thionyl, and the secondary battery, supercaps, hybrid caps, or a very special high power density batteries may be used. And these are really devices for asset tracking, like smart metering, equal bias tracking, agricultural monitoring, and so on. Here's an example which I brought to you. This is, I would call, a water meter, a smart water meter example, which was the very first one where we started to work on a project and started to deliver supercaps along with the battery to support the battery power back in 2002. So that's a really long time ago. That was probably the very first kind of like an IoT device. The definition IoT came a bit later, but actually these kind of devices were already used. Um, they were not named like the communication sequences were a bit like just like a GPRS, or it may be just an RF type of communication, but they certainly needed something to boost the battery power in order to make the reliable transmission. So let's take as an example this battery powered actually water meter that may be installed in your homes as well. Normally the size of the battery is a half AA to A size battery, normally lithium thionyl primary batteries. And for the example, just for the sake of simplicity, I was taking 50 milliamps for 10 seconds daily one times transmission, and the required lifetime without battery replacement 10 to 12 years. And the operating temperature is actually 0 to 55 Celsius degree in order to make sure that the water is not freezing. So there are different solutions. So this example I set as a marginal example. So here actually a battery only could actually do the job, or a battery with supercap powers, with supercap support may do the job as well. So let's dive into the details, how to distinguish and how to evaluate if you need supercaps or not for like a similar IoT powering device powering. In this example, Let's first see how it works with the one-time transmission per day. So here you can see that I was setting like a 20 microamps standard or constant current consumption, and the transmission period, which is normally 5 to 30 seconds, I was taking the 10-second period, 50 milliamps. And actually, the transmission cycle may differ depending on the application. Some applications requires multiple times a day transmission if it's like cow tag, like any type of animal tracking or bike tracking device, but it may be actually just one times a day or one times a week, depending on the like a metering device, depending on the utility company's protocols. So here actually the required energy, it's quite easy to calculate. So you need about 20 microamps for 10 years, which gets us to 1.75 ampere hours. And then for the required energy for the communication is actually 0.8 ampere hour if we talk about one day, or we take one per day transmission into consideration. But here's the big challenge with the batteries, that yeah, they operate a bit differently when we talk about 10 microamp versus 50 milliamps. So 50 milliamps may be potentially possible by the batteries if you talk about like a two-way size lithium titanium battery. So I was taking an example here, and you can see that the 50 milliamps could be delivered, but in case of that, actually there is an additional degradation of the battery. So you need to derate the battery, or you need to take into consideration, instead of 0.5 ampere hour, actually 0.85 ampere hour. So here the total energy consumption as we go is 2.6 ampere hour. That is like a standard size for a AA size lithium titanium battery. So with the one times per day transmission, it does the job. If you don't talk about very low temperatures. Now let's see the same with 2 times per day transmission. So 2 times a day will require, from the energy point of view, 1 ampere hour. With the similar, the rating will rise to 1.92 ampere hours. So altogether for the 10 years lifetime to get is 3.67 ampere hours. So here the AA size is not enough, so you need an A size battery, and that will certainly do the job. What if the application would require a lower temperature than 0 degrees? So if it's not a water meter, but it's maybe a gas meter, or it may be an industrial sensor somewhere installed on the field in like an oil and gas industry, and needs to deliver messages for a mission critical application or safety critical application. You see a bit more in detail how the lithium primary battery works. In terms of the temperatures as well, so we didn't consider the temperature effect yet for the calculations. We are taking in consideration water meter, which normally is installed in a place that doesn't go below freezing point for obvious reasons. Well, what if temperature sensor, or maybe a pressure sensor installed in the field and delivering mission critical or safety critical information, and it has to work maybe at minus 20 degree or minus, even below minus 20 Celsius degree. Then the battery will obviously suffer more during the operation, especially when it needs to deliver the current for the transmission. So as you can see, that there is a specific voltage plateau defined versus current and temperature for the batteries. So here you can see that the same 50 milliamps of power to deliver, the actually battery voltage at minus 20 Celsius degree would drop to just 3 volts, which often could be accepted by the transmission circuit. So depending on the transmission circuit, it normally works between 2.5 to 4 volt range. Some doesn't work below 3 volt, some allows even down to 2.5. But this is something certainly to be considered when you're making your battery selection and the circuit device, because the battery current capability and the voltage, the actual battery voltage, will really dependent on the temperature.
Yeah, it's a good reminder that the designer has to consider a lot of different factors. It's not just the total power consumption, but it's a power consumption across temperature. It's what is the peak power going to look like, and there's a lot of factors that go into designing that system to work, particularly for these long time periods.
Exactly. So let's see the same example with a different type of application that may require as well lower temperatures. But first, let's see just 2 times daily transmission with installing a supercapacitor. In terms of the energy consumption, we can take the same 10 years times 20 microamps, 1.75 ampere hours, and for the energy for the communication is 1 ampere hours with the 2 times 10-second transmission period. Here, since we have the supercapacitor, and the supercapacitor normally sized to deliver the total power of the pulse, actually the battery, we don't need to take into consideration this specific derating resulted by the heavier pulses, heavier current consumption, and that's why basically a 2.75 ampere hour battery could just do the job. So there's a chance that a AA size lithium tiny battery would just do the job with a supercapacitor installed in parallel.
And that's where, again, as we've discussed earlier, it's combining the best portions of each technology to solve the problem.
Exactly. But there are obviously some additional factors to be considered. Here you can see the basic supercapacitor model, which reveals a bit about how supercapacitors work. Because if you are connecting a supercapacitor in parallel with the battery, it obviously you need to consider some portion or some level of continuous current consumption, which is coming from the leakage current element of the supercapacitor. So normally the supercapacitor consists of a main capacitance in a series connection with basically the ESR, which is the internal resistance of the capacitors, and there is like a parallel resistor as far as the model goes, which represents the leakage current elements, and there are some dielectric absorption elements which normally for this type of application we don't need to really consider. It's really just makes a different behavior in case of the start of the operation. Let's dive a bit deeper into the leakage current of the supercapacitors, as it's basically the continuous energy consumption that has to be considered by the IoT, battery-powered IoT devices. And that's basically the major discussions which we have with our customers, as it needs to be seriously considered. So what is leakage current exactly? Leakage current is really something that shows a constant current, basically discharge after about 1,000 hours of operation. And while we get there from the 0 hour to 1,000 hours, there is a certain inflow current which is considered. It really doesn't need to be considered for the overall lifetime. So if you talk about a device that will work or it will design to be work from 10-15 years, but when it comes to like testing, most of our customers raise some questions about, oh, I get some samples and yeah, the leakage current is pretty high, and that's something which designers needs to basically understand, that the supercapacitors needs to be kind of like formatted. So you need to charge the capacitor for a long time in order to see where the true leakage current will show itself. So that's just a remark for the designers and whoever is about to test supercapacitors. Here you can see like how the leakage current versus temperature and voltage is distributed. Leakage current is heavily dependent on the temperature and the charge voltage actually. So you can see that there is exponential relation between these two factors. So the lower the temperature goes and the lower the voltage goes, it exponentially lowers the leakage current as well. So in case of your application, you always need to consider the full temperature profile. The voltage is pretty much given, so it's normally like a 3.6, 3.7 down to like 3 volts. But in terms of the temperature, obviously the overall profile needs to be considered by calculating actually the total consumption of the supercapacitors, that to be considered for the battery design as well. But our application engineer colleagues, we are happy to support you with accurate data on that. In terms of the sizing of the supercapacitors, normally we take into consideration some derating factors that often needs to be emphasized for designers. First of all, we actually calculate the required supercapacitor size according to the transmission current. So it's not like a nice rectangular pulse, but it's basically there is a specific power profile which we need to analyze in terms of to understand how much the total energy is and what are really the peak current points of during the discharge. And we are actually building normally a model in a calculation file in order to simulate how the discharge profile will work. And what we need to consider, and that's my strong recommendation, is take a look at your minimum temperature. So if you are designing it for a very low temperature, you need to look at the voltage plateau and the actual battery voltages at low temperature as they are dropping the voltage. So in case of a lithium thermal battery, if we take into consideration a minus 20, minus 30 Celsius degree operation, in Celsius degree, you may consider 3.1 volt. You need to also know how much is the transmission circuit cutoff voltage. In normally it's like 2.5 to 3 volts, so I was taking 2.5 here in this example. In terms of the supercapacitor, as it is a device which is similar to the batteries aging and losing capacitance and increasing the ESR over the lifetime, you need to consider somewhat like a minus 10% initial tolerance, as it's according to the normally specified datasheet numbers, and minus 30% capacitance loss over the lifetime. If you talk about like 15 years, normally industrial operation or installed outside of the field. Obviously, there are maybe some countries or areas like very high temperature areas in the southern regions that may need to consider a bit low, higher, maybe 35-40% capacitance loss and a bit more ESR increase. But overall, I would say for like in the US or European environments, this is the appropriate approach. And here, if I make this basically exercise, it results me to use two pieces of 3 farad supercapacitors in this case.
That's a good reminder that, from a designer's perspective, when you're starting with the typical numbers and then you start looking at the corner cases, the minimum voltage, the lowest temperatures, or the worst leakage if it's a high temperature, those corner cases can really degrade the performance and have to be planned for, or you get some bad surprises when you start putting this out in the field.
We have seen some bad results as well, or bad designs, but that's why we try to help customers and educate, and we are happy to share this information as well in order to avoid this to happen and have really robust, long working and satisfied end customers at the end of the day.
And are the graphs here that you show in the look like the from a computer, is that software that's available on your website, or is that just something you created yourself to run some simulations?
Yeah, actually, this is available as a calculation tool on our website. So it's called the SuperCap calculation. We obviously have. I'm normally using an Excel sheet in order to program the different type of discharge profiles. So we can help. Obviously, our engineers, field application engineers, can help customers with that. But you can, if you have a standard like discharge profile, you can approximate it to a specific constant current or constant voltage discharge, and you want to play with the numbers. This calculator is available at our website. Yes.
Very good.
So if I want to summarize actually what the options are here when we talk about a lower temperature application and multiple times of discharge or multiple times of transmission during one day, we get to basically 3 times or 2 times of 3 farad capacitors. And depending on which type of balancing structure we are using, because you need to balance the capacitors in order to provide them in order to prevent early lifetime failures, there might be different solutions. So if you have the standard passive balancing, it's out of the question because the power consumption would be way over the accepted values. So that's not really recommended. While you may find an active balancing like an open comparator that could result about 3 to 5 microamps of continuous discharge, that results about 0.35 ampere hour in addition to the battery capacity to be added. In case of supercap packs, which we normally sell for this kind of applications, those are two individual and matched cells with a slight balancing action in one package, like a PHV series. You can see that we can get about 2.3 microamps. So it basically consumes about 0.2 ampere hours from the battery over the lifetime of these 10 years. And there are more advanced technologies which we introduced this year, namely the PHVL series. That's a low self-discharge pack, and that gets us basically below 1 microamp, and very low, lower than 0.1 ampere hour consumption over the lifetime, or there are the new hybrid capacitors that even provides basically an incredible lower than zero point 0.1 microamp actually self-discharge, and this is just a single cell, very small as you can see, versus the other standard supercap solutions, and the power consumption is extremely low. In terms of the cost, it's comparable with the packs. Obviously, the packs and the hybrid capacitors cost a bit more than the others, but if you take into consideration the cost of the battery that you may need to and oversizing, it's not a question which is the best solution.
Yeah, then if you're even thinking about having to replace a battery or something, then you got total cost of ownership that really becomes an issue.
Yes, exactly. Overall, if you talk about the LoRa type of communication sequence or the communication protocol, you may or you may not need a supercapacitor. For narrowband, it's not a question. You need a supercapacitor or a hybrid supercapacitor. But for the LoRa, actually, with the daily one times transmission, no sub-zero temperature, you may be just best off without a supercapacitor, with a lithium primary tiny battery, for example. If the daily discharge or transmission is basically more than one times, then actually the battery needs to be oversized, and the standard AA battery plus a supercapacitor is a cheaper solution. Obviously, if you have multiple times daily transmission and you need to also support it in low temperatures, then you would need to oversize the battery significantly, and the cost would be significantly higher. Just for a reminder or a remark, the cost of the battery is significantly higher than the cost of the supercapacitor. So adding a supercapacitor may increase the battery cost with like 10%, and adding basically a size larger battery poses basically a significant cost increase. So in that cases, when you have multiple discharges and or transmissions per day and sub-zero temperatures, then the supercaps are really the best solution.
Well, very good. So as we get ready to wrap up for today, can you give us a summary and bring us home on this discussion?
Yes, so actually, thank you very much for listening. And so, if I may recommend you, you may use our online calculator to play a little bit with the numbers if you are designing some type of an IoT, battery powered IoT circuit. I certainly recommend you to take a look at the lithium thionyl batteries as a primary energy source, and consider supercaps or the hybrid supercapacitors for the secondary one, based on actually this table as you go forward. And if you need any further support, which normally required in terms of the precise energy consumption over the lifetime, or the actually taking into consideration a sophisticated discharge profiles, then our field application engineers are ready to support you.
And field application engineers just like you. So thanks for your time today.
Thank you very much, Dale, for the invitation.
So as we wrap up, we want to express our thanks to Mouser Electronics for their sponsorship of today's Tech Chat, and our senior FAE, Ekosh Labadi from Eaton, for teaching us about hybrid supercapacitors and supercaps for IoT applications. And be sure to join us next time on Tech Chat, where we chat with industry experts about the latest advancements in electronics technology. See you next time.